A strain gauge has many uses. It's common for measuring strain, but also in transducers that measure force, acceleration, and pressure. Strain is the change in length divided by the original length, and this is the axial strain. And strain is typically very small. For example, low strength steel, it yields at a strain of 0.0014. That is, it has plastic deformation at that level of strain. And so the term microstrain is commonly used, which is just the strain times 1 million. A strain gauge is a conductor, and its resistance changes with strain. So here's the resistance for a wire, rho L over A. Rho is the resistivity, which depends on the material and the temperature. L is the length of the conductor or wire, and A is the cross-sectional area. A strain gauge can also be used to measure stress. So if you have a structure and want to ensure that it's not overstressed, you can use this relationship and get stress from your strain measurement. So the stress is the product of the modulus of elasticity and the strain. This expression for resistance of the strain gauge, if we apply logarithmic differentiation, we get this term. We get this term here, which gives us the change in resistance in terms of changes in resistivity, length, and area. So we're going to assume a constant temperature, since that's not what we're measuring. In all applications, or not in some applications, temperature does change, but for now we're going to assume temperature is constant. So this term goes to 0. The next term, dl over L, is just the axial strain. And then the third term will start with this expression for area, and again apply logarithmic differentiation to get something for this. So we end up with dA over A is equal to 2 times dd over d. And this small change in diameter divided by the diameter is the transverse strain. So that's the definition of transverse strain. And transverse and axial strain are related by Poisson's ratio. So here's the expression relating transverse and axial strain. So we can just substitute that in there, and now we have dA over A in terms of axial strain. So we can substitute the definition of axial strain and then that expression we just found, rearrange it, and we get that the change in resistance divided by the resistance, then divided by the axial strain, is 1 plus 2 times Poisson's ratio for the material. And this is a constant, and it's known as the gauge factor. Strain gauges are typically used in Wheatstone bridges. The change in resistance is oftentimes small, and there are also other reasons to use a Wheatstone bridge, which we'll look at in a second. So here is the measured voltage, EG, for a Wheatstone bridge. E is the applied voltage. It should say ES because E could be kind of confusing since we're also talking in this video about modulus of elasticity. But anyway, this E is the applied voltage. And the gauge value before straining is given by this equation. We want to set up our Wheatstone bridge so that it's initially balanced. So the numerator here equals 0. And then here is this expression after straining. So R1 has changed to R1 plus delta R. Now we're going to expand that term and then get rid of this difference here because it's equal to 0 if our bridge was initially balanced. And also this change in resistance is small compared to all these other ones, so we'll get rid of that. Now our measured voltage is approximately equal to this term. Dividing through by R3 we get this, and we see that this ratio is equal to this ratio, and so we'll use that to get rid of R2 and R4 in our expression up here for the measured voltage. So now we have our measured voltage in terms of R1 and R4. And we can rearrange that to get the change in resistance in terms of our voltages and our unstrained resistance. And we had an expression for change of resistance in terms of strain, so now let's apply that. Okay, so here change of resistance over R divided by the axial strain is equal to the strain, the gauge factor. And this small change in R is approximately equal to the big change in R divided by R. So rearrange that, and we have now axial strain in terms of the measured voltage, etc. And here finally is an expression giving us strain in terms of our voltages and our unstrained resistances, and also the gauge factor F. So one thing that we assumed was that temperature was constant. That is not often the case, or that's often not the case. So in the configuration we have here, there could be a situation where we have no strain applied, but the temperature changes from whenever we had the temperature at which the bridge was balanced. And so then we'd get some measured voltage. And that would indicate that we had strain, but that would be a bad indication because there really isn't strain, there's just a change in temperature from our balanced state. So we can compensate for that by replacing R2 with an identical strain gauge. But it is not being strained, it's called a compensation gauge. So now any change in resistance due to temperature change, which affects the resistivity of the material, is canceled out on these sides. So if there's no strain here, any temperature fluctuations cancel out, and so we still measure 0. It still remains a balanced bridge whenever we have temperature compensation. So that makes one reason for using a Wheatstone bridge with strain gauges. Another configuration for a Wheatstone bridge is called a full Wheatstone bridge, and in that case we're using a strain gauge at every leg of the Wheatstone bridge. So in this case we can get better sensitivity for our change in voltage in terms with respect to change in strain. And here is the expression for measured voltage after straining, where we've had a change in resistance from all the strain gauges. And we're going to choose the resistors so that it's initially balanced. And so if they're initially balanced, then we end up with this expression. We end up with this expression regardless. If they're initially balanced, then we can cancel out these terms here. And we'll assume that these are small, and so this is approximately equal to what's shown here. And now we're going to find a common denominator, and we're going to divide both sides by R1 on the left and top and bottom by R4 on the right. Then we'll make the substitution that R4 over R1 is equal to R3 over R2, and that allows us to get a common denominator. And so we end up with this expression for our measured voltage in terms of our change in resistances. So how is this implemented typically? You can see if we have a cantilever load cell, we're measuring the force and we're using our strain gauges. So we have 2 on the top of the beam and 2 on the bottom. So these 2 gauges have positive strain and these 2 have negative strain. So these 2 will have a positive change in resistance and these 2 will have a negative change in resistance. Here's the shear and moment diagram. The shear is equal to the force P and the moment is P times L. The stress in this beam is given by moment times Y, which is the vertical distance from the neutral axis. In this case, Y is 1/2 the thickness because our strain gauges are at the, on the surface of the beam. And then the area moment of inertia is 1/12 W. W is the width of the beam times the thickness cubed. This is the stress, which we saw before is the product of modulus of elasticity and axial strain. So we can get an expression for the force in terms of the strain. Now, if we start out, if all 4 of these strain gauges are identical, then their unstrained resistance values are identical, and their gauge factors are identical, so their changes in resistance will be the same. Well, the two on the top will have the same positive change in resistance, and the two on the bottom will have the same negative resistance, which is just the same as the top multiplied by -1. So if we use that relationship or apply that relationship, then we can simplify this equation to the form seen here. So our gauge, or the measured voltage, is our supply voltage divided by the change in resistance over the nominal resistance. And this is just the product of the axial strain and the gauge factor. So what we were able to do with that is substitute for strain in terms of the voltages and the gauge factor. And this allows us a relatively sensitive means of measuring force with our voltmeter when we have a full Wheatstone bridge. And here it is, just simplified. Now, an example of using the strain gauge in a Wheatstone bridge. Say we have a strain gauge with temperature compensation where the nominal resistance is 120 ohms, and so we have 120 ohms on all the legs of the Wheatstone bridge. Two of the legs are strain gauges. Let me just show a figure for this. Okay, so this is our configuration. R1 is being strained and R2 is just there for temperature compensation. We have 1000 microstrain, and our Wheatstone bridge is supplied with 3 volts, and we want to find out what voltage is that we measured. So we have that the axial strain is given by this expression in terms of voltage, gauge factor, and resistance. And we can rearrange that to get the measured voltage. And plugging in the values from the problem, we have 0.001, which is our strain, times ES is 3 volts, gauge factor is 2.06, and R1 is the same as R4, which is 120, so 120 squared. And in the bottom we have, in the denominator, we have 240 squared. And so this ends up being 1.55 millivolts. And so the good thing about having this configuration is that we have temperature compensation, so that if our temperature changes, which will affect the resistance of our strain gauge, then we're not going to get a change in measured voltage because we have another strain gauge that's not being stressed, that's undergoing the same temperature change.